Okay, cool. Good afternoon, guys. So when we wrapped up on Friday, we kind of introduced this concept of timing diagrams and and logic hazards, right? We're talking about static hazards, dynamic hazards, and we're going to kind of build up a way of figuring out sort of what they, or how to detect them really is what we want to do now. So to do that, we're going to look at one example. So here we go. Let's say the example says this: consider following a logic circuit. Which looks like this. Well, it's already good, right? Did we do this one? It'd be to an inverter, 2 levels. Is this the circuit we did last time?
Yeah.
Okay, cool. Well, we're going to pick it up here anyway. So that's type A and C. I'll let you guys out here 2 rulers, right? All right. That output was to F, right? And we said that A equals C equals 1, and we were going to look at when B went from 1 to 0, right? So let's set up that timing diagram one more time. And of course, we already have this in your notes, just relax a little bit. So that's T in nanoseconds. Let's go ahead and say that our circuits have a propagation delay equal to 10 nanoseconds. So that's 10, 20, 30, 40, 50, 60, 70, 80. All right, and let's see that we've got what? Our output F, that's got a 0 and a 1. Our output, what do we call them? We call them D and E. Which has a 0 and a 1. D has a 0 and 1. And then finally, we were going to switch B, which has a 0 and a 1. So we said that B starts at 1. And let's go ahead and, I know we did this differently when we wrote the example last time, but just to make the graph look a little prettier, we'll say that B starts at 1, and at 20 nanoseconds switches to 0. Don't worry, like I said, this won't affect the outcome, right? Then when that happens, B was at 1, right? Which means that we had 0 and 1 here, which means that D was originally at 0 until the transition occurred. So we can say that D was equal to 0 until the transition occurred. Down here, C was equal to 1, and B was equal to 1, so E was equal to 1 until the transition occurred. And F being D or E, let's see, we have 0 and 1, means that F is equal to 1, again until the transition occurred. Now the switch from B equals 1 to B equals 0 affected D by sending, so B goes to 0, which means we have 1 and 1, which means the output D is 1, but it doesn't occur until after 20 nanoseconds, right? So we're going to pay 10 nanoseconds for the inverter and another 10 nanoseconds for the AND gate, which means it's another 20 nanoseconds from 20 to 40 before D catches up and clicks over to 1. So he goes from 0 to 1 and then hangs out. And then E. Let's see, B goes to 0, which means we have 0 and 1, which means that E goes to 0, right? But since there is no inverter here, we just have to pay the 10 nanoseconds delay at the AND gate. It means that E will switch from 1 to 0 at just 10 nanoseconds. Right, it'll stay there forever. Finally, F being an OR gate will stay at 1, but as we look at the transitions here, we have a place where D and E are both equal to 0, which means that F being equal to D or E will also go to 0, but not for another 10 nanoseconds. So it'll go to 0 at 40. And then here we have 1 or 0. So it will go to 1, but again, not for another 10 nanoseconds. And then it will stay at 1. So we have this condition where before the transition, F is equal to 1. At the end of the transition, F is equal to 1. So it should have been static 1, but we had a momentary bleep there where it went to 0, which makes this a static 1 hazard. It should have stayed at 1, but it clicked over to 0 really fast. And again, that can lead to all kinds of problems down the road. This is where we left off last time, right? Yeah. So the question now is, how do we detect these hazards ahead of time so that we can design them out of our circuits? And it turns out that we can do it by looking at the K-map for the circuit that we have. So this is, I know we used D and E, but there's only 3 inputs, A, B, and C to this circuit, which means that F is a function of 3 variables. So we'll draw a 3-variable Carnot map. Look at that, cut it in half, quarter it. We got F, we got A on the top, we got B, we got C, we got A equals 0 across the top row and 1, and then B and C is 0, 0, 0, 1, 1, 1, and 1, 0. Cool. So now, what do we have? How do we express F as a Boolean expression? Well, F is a function of A, B, and C. And here we see that what we had as D was B prime, since it goes to the inverter, and A. So we had A and B prime, or down here we just had B and C. So B and C. And remember a couple weeks ago we learned how to reverse engineer the K-map by looking at the Boolean expression. So here we're going to look at where A is equal to 1 and B is equal to 0. So since A is not inverted, B is inverted, A equals 1, B equals 0 in that binary notation, 1, 0. So A equals 1, B equals to 0 is going to be these top 2 rows on the right-hand side here. So it means we have a 1 there and a 1 there, and they are grouped. Or BC is going to be when B is equal to 1 and C equals to 1, but we don't care about A, so it's going to be these 2 rows. And it turns out that we can identify the places where logic hazards will occur. And first off, I should say, this assumes that all delays are equal, which in practice they are not in real life. Inverters tend to be a lot faster than AND gates and so on and so forth. But for the sake of sort of building up our kind of logic model, we assume that all propagation delays are the same. And logic hazards will appear wherever we have adjacent groups in the K-map. So we have a group here at 1, 0, 0, 1, 0, 1, and a group here at 1, 1, 1. There's an adjacency between these 2, which means that a logic hazard exists from between 1, 0, 1, right, this cell, and this cell. 1, 1, 1. 1, 1, 1. But at that transition, that's where it'll occur. And let's see, f should be 1 in those places. Get my thoughts together. 1, it stays at 1. We went from b equals 1 to 0. And specifically, when we're grouping 1s, the transition will occur when we go from 1 to 0, which is exactly what we saw here. So let me rewrite that actually. It exists from 1, 1, 1 becoming 1, 0, 1. So when b goes from 1 to 0, the logic hazard exists. So we find it by looking for adjacencies in our groups. Cool. And that's what we saw here, right? There's an adjacent group between the two of these guys. When b goes from 1 to 0, we transition b from 1 to 0, and we set a and c equal to 1, which is what happens here in both cases. And we saw that we got a logic hazard. Now the way that we get our logic hazards out is by creating those consensus terms. Right? Remember that we talked about if you have terms that are already grouped up, and you make a group that sort of combines two, what you'll get is the consensus term of both of these terms. Right? We can demonstrate that. So this group here gets us what? Well, it's a equals 1 and c equals 1. So it's going to be or AC. And if we apply the consensus theory across b prime, and b, the consensus term is AC, right, which is the redundant term. So we're going to add back a redundant term to our logic circuit. And it's redundant, meaning it doesn't affect the truth table, but what it will do is protect us from logic hazards. So we're going to sacrifice a little bit of efficiency for safety. So what we do is take this circuit and add in a gate. That takes as its inputs, right, and an AND gate specifically, A and C. And while this is redundant in terms of the truth table, this will prevent that guy from happening, right? Which makes an intuitive sense because F is or all of these terms, and A and C are the ones that always stay the same, right? We always have A and C locked at 1 in our example, which means that this guy will stay locked at 1, which means that the output F, it doesn't matter what these guys are, will always be equal to 1. So it sort of nulls out that hazard. Yeah, the guys on the Discord, the stream has just been spotty all afternoon. I don't know if it's an issue with the Wi-Fi here at Holden Hall or if it's an issue with my laptop. But it's been, like I said, it's been kind of going in and out all day. Thankfully, we're still recording, and the recording is separate from the stream, so I'll upload the videos to YouTube this afternoon, and you should be okay. So, any questions about this example?
So if you have more than just two terms of the expression, then how do you know which ones to use to make the consensus term?
What do you mean?
So, like, this expression is just A, B naught, or B, C.
Right.
So you can use the consensus term with those two.
Right.
They're the only two in the expression.
Yeah.
But, like, say you added a third expression, like, or.
Oh, okay. Well, that would be another logic hazard, right? So if, it's hard to illustrate with this. Let's move on to the next example, and we'll kind of address that point.
Okay.
Okay. Any other questions about this example? Okay. let's suppose that we want to make a circuit out of NOR gates. Now, to make a circuit out of NOR gates, we have to start with what coming out of our K-map? Remember, to convert a circuit of AND and OR into NAND gates, you got to end with an OR gate, which means you got to start with a sum of products expression. And to convert a circuit into a circuit of NOR gates, you got to start with an AND gate at the beginning, which means you got to have a product of sums expression. So let's say that we wanted to do this, indeed. I can't draw something. A function of 4 variables. F. We got A, B on top, and C, D. So we have A, B 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. And we had this business. We had 0, 0, 0, 0, and that's in a group. And we had 0, 0, 0, 0, and that's in a group. And we had 0, 0. With those guys in here. And the ones everywhere else, but I won't draw them. So here we can say that f is a function of 4 variables, A, B, C, and D. And this is going to lead us to the product of sums expression. From this first group, we've got A equals 0 and C equals 0, which means that, remember, everything is flipped. So that'll be A or C. And then here, we have A equals 1 and D equals 1, so that we're going to have A prime or D prime. And then finally, we have what? We have B equals 1 and CD is 1, 0. So that's going to be B prime, C prime, or D. B prime or C prime or D. Now here we're going to be looking for all the places where they're adjacent. This comes back to your question, and that is anywhere there is an adjacency between groups, there will exist a logic hazard. So for example, let's list them all out. So logic hazards, we're going to have one here connecting these two groups. That's going to be 1, 1, 0, 1, and 0, 1, 0, 1. We'll have a hazard here between these two groups. That's going to be 1, 1, 1, 1. And what is this? 1, 1, 0, 1. Let's see. We're going to have a hazard connecting. Remember, a 4 variable K-map can connect to the outside. So between these guys, so the same terms, but even on a different sort of section, right? 1, 0, 0, 1 right here, and 0, 0, 0, 1. We'll also have a logic hazard. Excuse me. And then finally, down here, remember, they connect, there's adjacency from top to bottom. So from 0, 1, 0, 0 to 0, 1, 1, 0. So in this circuit, brings us 4 different places for logic hazards to be.
I think it's time to just close circuit.
Time to design something else, right? All right. So first, let's just go ahead and take a look at one of these. And we can pick which one we want. I don't know which one of these you want to do.
The first one.
First one? Let's do the first one. So let's take a look. Let's draw the circuit. And I'll do the timing diagram here. So I'll draw the circuit right here. So we've got, what kind of split the difference here? 3 OR gates. All feed into an AND gate. And the first one has A and C. Now, it's important to remember when we're designing the logic circuit, not really caring about our propagation delays or our logic hazards, we ignore the inverters, right? But the inverters are going to play an important role, so we need to, when we're discussing logic hazards, we do want to go ahead and include them. So we got what, A and D, both of which are going into an inverter. And then here we have B prime, C prime, and D, so it's going to be B, C, both through an inverter, and then D without the inverter. We'll play the same rules, we'll still say it's 10 nanoseconds per. And since we're doing this top one, we're going to say what? That B and D are going to be equal to 1. C is going to be equal to 0. And we will take A from 1 to 0. See what happens. So we get a horizontal axis, which gives us time in nanoseconds. We'll do 10 nanosecond steps. All right. Now we go ahead and label each of our gates. Let's see, we have F down here on the bottom. That's got a 0 and a 1. Let's just label our gates G1, G2, and G3. I'll list them up here in reverse order. We'll say G3, G2, that's 0, 1, that's 0, 1. G1, that's 0 and 1. And then finally, what is the variable that we're changing? We're changing A. That's 0, and that's 1. Okay, so we're going to switch A from 1 to 0. So we'll go ahead and labels here 10, 20, 30, 40, 50, 60, 70, 80. Let's say that we're going to go 20 nanoseconds and then do the transition. So A starts at 1. At 20 nanoseconds, it clicks to 0 and continues on forever. So let's see. G1 in the beginning, C is equal to 0, and A was equal to 1, which means that G1 was equal to what? It's equal to 1. So G1 is going to start its life as 1. And then A switches to 0, which means that G1 is also going to switch to 0, since 0 or 0 is equal to 0. So it's going to switch to 0, but it's going to take 10 nanoseconds to do it. So at 30 nanoseconds, G1 will switch to 0 and stay there. Now let's take a look at G2. G2 began its life. Let's see, A was equal to 1. D was equal to 1. They both went through inverters, which means we had 0 and 0, which means that G2 started its life at 0 until the transition occurred. So G2 goes at 0. And then A switches to 0, which means the input to the OR gate switches to 1, which means G2 switches to 1. But it's going to take 20 nanoseconds to get there, right? because the transition took place through the inverter and through the OR gate, right? We have to pay 10 nanoseconds for each gate that we hit. So G2 is going to switch from 0 to 1, but not until the 40 nanosecond mark. All right, let's take a look at G3. So we started with B is equal to 1, C is equal to 0, and D was equal to 1, which means that we had, what, 0, 1, 1 on the entire thing, which means that it starts out at 1, right, because it's an OR gate. So G3 started at 1 until the transition. Now, is G3 affected at all by the transition? No, it isn't, right? Because the input to gate 3 is just from B, C, and D, and those are staying static, and we're only changing A, right? So G3 isn't even affected at all by the output. All right, so let's take a look at F. So F coming out of the gate, G1 is 1, G2 is 0, and G3 is 1, which means that F was equal to what? Was equal to 0, right? That's going to stay here until the 30 nanosecond mark. At which point, G goes to 0, G2 is still 0, and G3 is still 1. So that means that F stays at 0. And here, this next one, we've got 0, 1, and 1, which means that AND still stays at 1. So what happened? Nothing happened, right? But something was supposed to happen, right? We identified that a logic hazard was supposed to appear here. Weren't we? Yeah. The logic hazard didn't happen. What's the deal? Well, the deal is that the order matters, right? The logic hazard exists at the transition, but it doesn't always exist in both directions, right? So now let's take a look at, so first off, does everyone understand what happened here? Right? We identified a place where a logic hazard should have existed. We simulated it by hand and found that nothing happened, right? What's that?
It seems like nothing would happen on any of them except for the second one on the left. Because they've all got at least 1 0 in it, and it ends with an AND gate.
That's what I'm saying. Yeah, I'm saying nothing happened.
Yeah, but like, wouldn't the only one that didn't, like the only one that would turn on would be the second one on the left side, the 1 1 1.
The second one, what do you mean? This one?
The 1 1 1 1. Yeah. I feel like that's the only one where it would turn on.
Why do you feel that way?
Well, because it's an AND gate at the very end.
Yeah.
And for an AND gate for it to turn on, they all the inputs have to be 1.
Well, remember, it's not and all of these, right? It's and through these logic gates, right? So it's this and this and this, right? There's a little bit more to it
Okay.
than just that, yeah.
So they're switching because of the,
Yeah, they're switching because of the logic gates.
yeah, but they switch because we've got some primes in there, some inverters.
Yeah.
Okay.
Yeah, right. So this, hold on. So this is the input to the system, but that's not what happens here, right?
Yeah.
Right here, there's the Boolean expression that we figured out, right? It's this thing
Mm-hmm.
that's up here, right? That's what affects the output.
Mm-hmm. Okay, I see what you're saying.
You sure?
Mm-hmm.
Okay. All right. So what I'm going to do now is let's take a look at it in the other direction. So I think we can we'll leave A the way it was. Well, we're going to flip it, so I guess we're going to erase A. We can leave G3 where it is, since G3 doesn't care about anything. But we need to take care of the rest of these guys. So instead of going from 1 to 0, let's go from 0 to 1. Let's see what that does. So we're going to leave everything exactly the same, except we're going to take A starting at 0, and at 20 nanoseconds, we're going to take it to 1, and then we're going to bring it over. So, let's say, so G1 starts at 0, 0 now, which means it starts at 0 until the transition. Then A goes to 1, which means that G1 goes to 1. But not for 10 nanoseconds, so that won't be until the 30 nanosecond spot. Yeah. So there, and then we'll stay there. G2 will be, let's see, D is 1. What do we start with? We start with A equals 0. G2 is going to start with 1. Yeah. Since A is equal to 0, so it's 1, 1, 0, 1, 0 is 1. So at the start of the life, until the transition, it's going to be at 1. And then A goes to 1, which means it goes to 0, which means G2 is going to go to 0. But remember, it's going to take the full 20 nanoseconds to get there, since there are 2 gates involved in that transition, meaning that it won't switch until 40 nanoseconds, at which time it switches to 0. And G3 is still doing its thing because G3 doesn't care. So now we go back and take a look at F, and F is ANDing all of these. So we've got what? We've got 0 and 1 and 1. So F is going to start at 0 until the first something happens. It happens here, where here we have 1 and 1 and 1. So F is going to click up to 1 until here, the next transition. Wait, I'm screwing up. What did I mess up? I didn't do the delay, yeah. All right. So it's still going to wait 10 nanoseconds, and then go to 1. And we get this another transition where now we have 1, 0, and 1. So it should go back to 0, but not for another 10 nanoseconds. And there we go. So here we have 0, 1, 0. So a logic hazard does exist. What logic hazard is this? What type is it?
Static 0.
Yep, you're absolutely right. It should be a static 0. So static means only one hazard occurred. The next number is what it should have been, so a static 0 hazard. Someone on Discord says there was a typo, that this one, let's see, 111 and 1110. Oh, you're totally right. Good catch. Who was that? Aaron, good. This cell is 1110, not 1101. All right. So yeah, so this shows that the same junction, the same presence of the hazard, it depends on which direction you're going for the hazard to occur. It won't always be on both of them, but it will be on one of them. Cool? Any questions about that?
So shouldn't you fix the arrows then to, like, where the arrow points in which direction it goes? With the both arrows, it makes it seem like
Yeah, I guess you're right.
that's the way for the logic hazard to happen.
Well, usually, yeah, so you're right. The logic hazard exists in the transition from that guy to that guy. Most of the time, we won't take the time to figure out which one is which, right? We'll just cover that up to get rid of the logic hazard. So how do we fix this circuit to get rid of our logic hazards?
Do it the other way.
What's that?
We did do it the way we did it the first time?
No, because that's the input to the system. We can't control that. We design our system to not have those adjacencies. So the first thing we'll do is you just gotta look and see, all right, where is stuff adjacent? We gotta cap stuff off, right? So the first thing is that we've got adjacencies between these cells, right? So what we'll do is this, we'll go, I'll take a group of 4 here. Again, this is gonna give us a not optimized result, but this term will cover up these 2 logic hazards. So what is that gonna get us? That's gonna get us CD is 0, 1. So we're going to tack on to our original expression here an OR, what was it, 0, 1? So it's going to be C or D prime. Which, of course, if you look at these first 2 terms, A or C and A prime or D prime, C or D prime is, of course, the consensus term between these 2 guys. Next up, let's do, we've got to group these guys. We'll do a group 2 here. And that'll be what? 1, 1, and C is equal to 1. So that'll be A prime or B prime or C prime. One. And then finally, I've got to cover that one, which is 0, 1, and then D is equal to 0. So A is 0, B is 1, D is 0. So it's going to be A or B prime or D. Just like that. So yeah, so we added on 3 additional sum terms, which arguably adds a lot to our circuit, but it cuts out those logic hazards. And again, the decision of what is worthwhile, is it worth it to add these terms to cover the logic hazards, kind of depend on what the application is and what the consequences of the logic hazard are, right? If the consequences of the logic hazard are, a few rounding errors in a calculator, it's probably better to just go with the more optimized solution, right? But of course, if the logic hazard means the missile explodes in the silo instead of, where it's supposed to be, then you probably want to cover up those logic hazards. So,
how would you know, like, what the logic hazard is going to do? I mean, I guess that's...
well, you're going to look and see what your circuit is attached to, right? So
Yeah.
you made this part, right? But your system is going to be part of a much larger system, right?
Mm-hmm.
So you're going to have to see, you sit down with the guys who designed this part and say, all right, well, if my output throws a static 0 hazard, what's going to happen here? Yeah.
Okay.
Would it be quicker just to add like a slight delay in the processing of the answer? So
Yeah, what you'll see a lot in practice. Remember that all this business of logic hazards assumes that all the propagation delays are the same, which they won't be. What you'll see a lot of times is people adding buffers or like 2 inverters, right, in between these gates to like get the delays just right. So that way the solutions are still kind of optimized by the gates, but are the timing works out, so you don't have those issues.
Whenever you worked at TI, how often did you have to deal with logic hazards? Every day? You ever did?
No, but for what it's worth, I wasn't an ASIC designer, I was a test engineer.
Mm-hmm.
And so it didn't come up a ton. And in fact, I don't think it came up at all, particularly in my job. But again, the project I worked on while I was there I was working on an analog thing, so
Oh, yeah.
of all bits, yeah. All right.
Do you know if anything like this could happen when you're like coding software, or is this purely a hardware issue?
Ooh, I've never thought about it before, but I would imagine, yeah. Well, we used to call them race wars, but you can't say that anymore. Race conditions. Are you familiar with race conditions in software engineering? Race condition. So race condition is when, say that you have 2 bits of code that both work with the same object in the database, right? And so a race condition is if they both work with that, depending on what they do, they can manipulate the database thing in an order that is not what you wanted, right? Especially if everything is asynchronous, right? If I have an asynchronous function and an asynchronous function, and I want to do function 1 to the database and then function 2, but it's both asynchronous, then you have a race condition, which means that function 2 might beat function 1 to the database, in which case your stuff will be out of order, which is, yeah, arguably kind of exactly what we're talking about here. Yeah. I mean, the signals are arriving in an order that kind of screws up your output. Yeah. So there you go, there's my answer. Race conditions is the software engineering equivalent of logic hazards.
So it's kind of like those like mazes that people build. What are they called? Where you like knock the dominoes over and then
Like a Rube Goldberg machine?
What's it called?
A Rube Goldberg machine?
Yeah.
Like a bunch of crazy stuff happens and they like crack an egg or something at the end?
Yeah.
Yeah.
Kind of like that.
Yeah. Yeah, I can see that.
Because if the timing's messed up, then then it won't crack the egg at the end. Like if this die falls at this before the other one's got to it, then it messed it up.
Absolutely, yeah. Yeah. Like I said, that's why I said practice, designers will just like throw buffers and stuff in all the places to get the timing to work out just fine. Right? So, all right. Any questions about any of that? Cool. Well, that's all we had for you guys today. That is it for Chapter 8. We will pick up in Chapter 9 on Wednesday, where we're going to talk about some cool stuff. Much more computer architecture-y stuff. We're kind of getting out of the theoretical side of things and getting into more hands-on applied side, which is, I'm sure, a thing you guys are looking forward to. So yeah, I'll see you guys on Wednesday.
Later in the semester.